three metals, calcium, barium, and strontium, occur in the same family on the periodic table and have many similarities in properties. They all form hydroxides with alkaline characteristics and have long been known as the alkaline earth metals. In these test tubes, we have samples of the carbonates of barium, calcium, and strontium, respectively. Now, in order to keep these three straight during the experiment, remember that the tubes are arranged in alphabetical order from left to right, with barium on the left, calcium in the middle, and strontium on the right. We will now add 5 milliliters of dilute hydrochloric acid to each tube and note the reaction. Recall that carbonates usually react with hydrochloric acid with effervescence. All three carbonates have reacted similarly with the hydrochloric acid, having dissolved, and this means that the chlorides of barium, calcium, and strontium are all soluble. Now to each tube we'll add a few drops of dilute sulfuric acid to test the solubility of the sulfates. And here we discover a difference, because barium and strontium sulfates are very insoluble and formed almost immediately, while calcium sulfate is much less soluble and only forms slowly and then in much smaller amounts. In the 3 test tubes, we had placed samples of barium, calcium, and strontium carbonates, to which we added hydrochloric acid. The reactions in all 3 cases are entirely similar, and we obtained solutions of the respective chlorides, water, and carbon dioxide. Then to solutions of the chlorides, we added some dilute sulfuric acid as a source of sulfate ion. In the case of barium and strontium sulfate, a precipitate was obtained immediately because the solubility product constants for these 2 sulfates are very small, 10 to the minus 10th, 10 to the minus 7th. In the case of calcium sulfate, the precipitate formed rather slowly, since calcium sulfate is much more soluble, having a solubility product constant of about 10 to the minus 4th. We will now demonstrate the different colored flames that barium, calcium, and strontium ions give when solutions containing them are placed on platinum wires and held in the flame of the Bunsen burner. The lights have now been turned out so that we can see the characteristic colors of the flames due to each ion. First, we will test a solution containing the barium ion. You should notice the greenish-yellow flame imparted to the Bunsen burner flame by the barium ion. Next, we will test the calcium ion. This flame, which is rather brief in duration, is generally described as orange-red. And last, we'll test the strontium ion. This ion gives a longer-lasting crimson flame. In the test tube, we've placed a solution of calcium hydroxide. The tube leading down into the liquid is attached to a carbon dioxide generator. We will now put the generator into operation and cause carbon dioxide gas to bubble through the liquid in the tube. In a few minutes, you will see the white precipitate of calcium carbonate beginning to form. Precipitation will continue until virtually all of the calcium has been converted to calcium carbonate, which will remain suspended as the white solid in the liquid. Now, as we continue to bubble carbon dioxide into the tube, the calcium carbonate will slowly dissolve, forming calcium bicarbonate, and the solution in the tube will again become clear. In the test tube, we placed a solution of calcium hydroxide. Then we added carbon dioxide gas and precipitated calcium carbonate. And then we illustrated that when calcium carbonate solid is exposed to solutions containing dissolved carbon dioxide, the calcium carbonate dissolves with the formation of calcium bicarbonate. This is what happens when rainwater containing these substances trickles over limestone rock. And this is the source of much of the calcium ion found in hard waters. We will now examine the reaction of metallic potassium with water. In this beaker, we place some distilled water to which has already been added some phenolphthalein. The test tube has been filled with this distilled water phenolphthalein mixture and then inverted in the tube. Now I'm going to drop in a small piece of metallic calcium and place the tube over the calcium. You'll notice that the solution immediately becomes red, indicating that calcium hydroxide has been formed, and the tube is rapidly filled with gas. The test tube is now filled with hydrogen, and we will demonstrate that it is hydrogen by mixing it with air and igniting it. The Erlenmeyer flask, simply filled with air, we'll place the test tube mouth to mouth with the flask and then invert the setup so that the hydrogen will diffuse rather rapidly up into the flask and the air will pass down to the test tube. Now we'll light a wooden splint at the Bunsen burner, place the tube in the flask, and from the explosions that we obtained, hydrogen was obviously formed when the calcium reacted with the water in the beaker, along with calcium hydroxide. You will recall that in the beaker we placed water containing phenolphthalein and then added a piece of metallic calcium. Hydrogen was evolved rapidly, and the phenolphthalein turned red, indicating the presence of calcium hydroxide. We collected the hydrogen over water, then mixed it with air and ignited it. An explosion took place as a result of the reaction between the hydrogen and oxygen to form water. Industrially, calcium oxide, or quicklime, is prepared by heating calcium carbonate to a high temperature. In the lab, we can accomplish this transformation with the Bunsen burner. On the wire gauze, we have placed a small marble chip. Marble, of course, is calcium carbonate. And we are heating the chip in the flame of the burner. The chip is slowly being converted from calcium carbonate to calcium oxide. In the two test tubes, we've placed some distilled water, and we have added some phenolphthalein to each tube. To the tube on the right, I will drop or add a marble chip which has not been heated. And you will notice that nothing much happens. Calcium carbonate, then, does not react with water containing phenolphthalein. Now to the tube on the left, we will add the marble chip which has been heated. And if, as we suspect, calcium oxide has been formed during the heating, it should react with the water to form calcium hydroxide, which should turn the phenolphthalein pink. The instant appearance of the pink color indicates that calcium oxide was formed when the calcium carbonate chip was heated. Calcium carbonate here represents the marble chip, which we heated to a very high temperature with the Bunsen burner, causing some decomposition into calcium oxide and carbon dioxide. After the chip had cooled, we then dropped it into a little distilled water containing phenolphthalein, and immediately we saw the phenolphthalein turn red as the water reacted with the calcium oxide, forming calcium hydroxide, the OH ions of which caused the phenolphthalein to change from its colorless to its red color. When the ions of calcium or magnesium appear in ordinary tap water, the water is said to be hard. Chemists distinguish two kinds of hardness, however: permanent hardness, which is caused by calcium and or magnesium ions present as their sulfate or chloride, and temporary hardness, which contains calcium and or magnesium ions as the bicarbonate. The reason for these names is that permanent hardness is not removed by boiling the water, whereas most of the temporary hardness is removed by boiling. Calcium and magnesium ions react with soap to form a precipitate. Hard water, therefore, requires a considerable amount of soap because much of the first portions of soap combine with the calcium and magnesium and are removed from the solution. We will demonstrate the reaction of these ions with soap in the two tubes in the setup. The tube on the left contains tap water, and the tube on the right, distilled water. To each tube, we will add several drops of soap solution. You notice that no precipitate appears with the distilled water, but in the tube containing the tap water, a milky substance is formed. This is the precipitate caused when the calcium and magnesium ions in the tap water react with the soap. Now we'll place a stopper in each tube and shake vigorously. In the tube containing the distilled water, we have lots of soap suds. But when we shake the tube containing the tap water, practically no suds is obtained. This is because the calcium and magnesium in the tap water precipitated most of the soap. Now, if we added more and more and more soap to this tube, we could eventually obtain suds. And this is, in effect, what you do when you wash in hard water. One way to remove the offending ions of calcium and magnesium from hard water is through the use of materials called ion exchange resins. Let this heavy line represent a very large organic molecule, polystyrene, which has been sulfonated at various positions to give sulfonic acid groups. And then the hydrogen associated with the sulfonic acid group has been replaced with sodium ions. The large polystyrene backbone makes the whole molecule insoluble, but the sodium sulfonic acid groups sort of stick out into the solution. And when water containing calcium ion trickles down over such a resin, the sodium ions are displaced. The calcium ion becomes associated with the two sulfonic acid groups, and the sodium ions are released into solution. And since sodium ions don't react with soap, the water has been effectively softened. Now we're going to demonstrate this phenomena in the next sequence on the film. But we're not going to use calcium ion in our ion exchange experiment because the calcium ion is colorless and the sodium ions are colorless, and it would be very difficult to follow the course of the reaction. Instead, we're going to use the copper-ammonia complex ion, which is dark blue in color. The color permits us to identify this ion, and which is in equilibrium with a small amount of copper ion and ammonia. Now, the copper ion will react here in exactly the same way that the calcium ion did, and will become associated with the sulfonic acid groups, and sodium ions will be released. Therefore, when a solution containing the equilibrium mixture, copper-ammonia complex and copper ions and ammonia, flows down through an ion exchange resin tube, the copper ions should be removed from the equilibrium. And this, of course, will cause the complex ion to dissociate. And the filtrate, or liquid being produced at the lower end of the tube, should contain sodium ions and ammonia. The ammonia can be tested for because of its basic properties. We will now demonstrate one of these ion exchange columns in action. As we have just discussed, we've seen that it's possible to remove offending positive ions from solution using a cation exchange resin. Now, in this tube, we have some cation exchange resin, essentially a sulfonated polystyrene, in which the hydrogen ions on the sulfonic acid groups have been replaced with sodium ions. In this bottle, we have a solution of cupric ammonium sulfate, and the only part that we're interested in is the copper-ammonia complex ion. We're using this ion because of its blue color, which permits us to follow the series of events as they take place. Now, we'll add some of this solution to the ion exchange resin in the tube. I think you can clearly see the blue color of the solution in the upper part of the tube, but notice that the emerging liquid at the bottom is colorless. Now, in the tube, we have the equilibrium between the cupric ion and the copper-ammonia complex, and the ion exchange resin is removing the copper ion, replacing it with two sodium ions. The ammonia, which is another product of the reaction, and the two sodium ions should pass into the collecting tube. Now, the sodium ions we can't test for, but the ammonium ions should give a pink color with phenolphthalein. So as we add phenolphthalein to this tube, we see the immediate formation of the pink color, indicating that ammonia has emerged from the bottom of the ion exchange column. We will now proceed to show how we can calculate the total hardness in a sample of hard water. In this experiment, both the calcium and magnesium present will be calculated in parts per million of calcium carbonate. In this flask, we've placed 50 milliliters of Akron tap water, and we will add this to the small Erlenmeyer flask. Next, we will add some indicator. The indicator we're using here is called Univer and forms a purplish-red colored complex with calcium and magnesium ions. We'll swirl to dissolve the indicator. The color of the solution indicates that calcium and/or magnesium are present. The burette, which this time is a 10 ml burette instead of the usual 50, has been filled with a solution of versine and the level adjusted to 0. Versine is a chemical compound which itself forms a complex with calcium and magnesium ions. Now, as we add the versine solution in small batches to the flask, the versine will form a complex with the calcium and magnesium, and remove those ions from their complex with the indicator. The endpoint is signaled by the appearance of a blue color, which is the color given by the indicator in the presence of very small amounts of calcium and magnesium present in equilibrium with the versine. This particular versine solution has been made up in such a way that when we use a 50 ml sample of tap water, the parts per million of calcium carbonate are given by multiplying the milliliters of versine used by 20. I think you can see that the original pink color of the indicator is beginning to disappear. And the endpoint appears when the color of the indicator changes to a purplish blue color. This is the endpoint of this titration. As I said before, this is a 10 ml burette. This is the 4.5 ml mark. This is the 5 ml mark. The level of the liquid in the burette can be carefully noted and determined to be 4.80 milliliters. To calculate total hardness, we need to know the volume of our versine solution used and the strength or titer of the versine. Now, this particular versine has been made up in such a way that each milliliter of versine used represents 20 parts per million of hardness in water, figured as calcium carbonate, when we deal with a 50 ml sample of hard water. And this was the size of the sample that we used. So we need only multiply the volume of the versine used by 20 to find that the total hardness in Akron tap water in this experiment is about 96 parts per million. This means that if we had 1 million pounds of Akron tap water, we would expect to find dissolved therein about 96 pounds of calcium carbonate or its equivalent in calcium bicarbonate. We will now calculate the permanent hardness in soft water by this device. With the versine univer mixture, we titrated total hardness. Now, in this burette, we've placed some hydrochloric acid. We'll titrate a sample of tap water with the hydrochloric acid, which will titrate the carbonates. And assuming that all the carbonates are calcium carbonate, we can calculate temporary hardness. And permanent hardness may then be calculated by subtracting the temporary hardness from the total hardness. In the graduated cylinder, we've again placed 50 milliliters of Akron tap water. We will add that to the Erlenmeyer flask. The indicator of choice in this experiment is methyl red indicator, which has a yellow color on the basic side and a reddish pink color on its acid side. In the burette, we have some 0.015 normal hydrochloric acid. The burette has been filled and adjusted to 0. You can see the pink color of the indicator beginning to appear. The appearance of the permanent pink color signals the endpoint of the titration. At the end of the titration, we can read the volume of acid used. Again, we are using the 10 ml burette. This is the 2.5 milliliter line. This is the 3 milliliter line. The reading, when taken, is found to be 2.87 milliliters of HCl used. From our titration data, we can now proceed to calculate the temporary hardness of our sample of tap water, and from this data, then, the permanent hardness. Recall our old titration experiment rule that at the endpoint, the equivalence of acid used always equals the equivalence of base used. Now, in this experiment, we know that we used 2.87 milliliters, or 0.00287 liters, of 0.015 normal acid. The equivalence of base, then, equals the product of these two numbers, or 0.4043, or 4.3 times 10 to the minus 5, equivalence of base. Now, we know that this much base was present in a volume of 50 milliliters of tap water, which was the quantity we measured out. And we need to know how many grams of base, not equivalents, are present in 1 million milliliters of tap water. This will be our hardness in parts per million. Well, the equivalent weight of calcium carbonate is 50. So we multiply the gram equivalent weight, 50, times the number of equivalents present. This will give us the number of grams of calcium carbonate present in 50 milliliters of the solution. And we want to know how many grams are present in a million milliliters. In solving this equation for X, we find that 43 grams of calcium carbonate would be present in 1 million milliliters of this solution, or that the hardness, then, on the calcium carbonate scale is 43 parts per million. Now, this figure permits us to calculate permanent hardness, because our univer versine titration told us that the total hardness was 96 parts per million. We've now found temporary hardness to be 43 parts per million. Permanent hardness must be the difference, or 53 parts per million. In this film, then, we have examined several of the important reactions of calcium, barium, and strontium ions. We've seen how hard water is caused by the presence of these ions, and we've examined a method or two for removing them from water. Finally, we've examined methods by which the chemist can tell how hard a sample of water is, both with respect to its total, permanent, and temporary hardness.